Alright everyone, we're going to go through chapter 8 and we're going to go through this again with the mindset of this is just a guide to see all the answers to the examples, and although we'll cover everything, it won't be as in detail as we did in the live lecture. But here we go. Really, this first section is just getting acclimated to your calculator. So honestly, the goal of this section is to be able to plug each one of these into your calculator and be able to get the right answer. There's actually no 8.1 questions on your exam, but 8.1, of course, is the lead in that brings us to where we're going. And it is nice to use your calculator at some time. So the main thing we need to do is just solve each root. And remember that here's what a square root is saying. It's saying it's saying, is there a number that you can multiply together twice? There's an invisible 2 here, square root, just like there's a visible 3 here, there's an invisible 2 everywhere else. So is there a number that I can multiply together twice to get this number 169? And it turns out there is, and the answer is 13. So you're just plugging that into your calculator and getting that answer. This next one is a little bit trickier, but it's going to be negative 0.7. Now, a lot of us, here, let's do the next one, then talk about that. The square root of negative 100 is going to be no real solution. Alright, now why is that? Well, let's see here. Because your options are either negative 10 times negative 10, a number times itself, but that ends up making positive 100. I guess your only other option is positive 10 times positive 10, but that also makes positive 100. So there's no way you can multiply the same thing to itself twice and get negative 100 with real numbers. So there's no real solution. So then what's going on with this example above? Well, the negative is on the outside of the root. It's saying, hey, deal with the inside of the root, which I did. I used a calculator, got 0.7. And then the negative is going to tag along because it was on the outside, so keep it on the outside. So just be aware of that if there's a negative on the outside, it just tags along. If there's negative on the inside, now you have a question of, is it actually possible? Again, your calculator will confirm that. Alright, let's keep going. This one, same idea. Copy the symbols on the outside. Plus or minus 12. Next one, we've got fractions. Now this one, although you could do it with your calculator, it might spit out a decimal. What you should more so notice is that, hey, why don't I root the top, which is 7, why don't I root the bottom, which is 12, and put them back over each other, because that's where they came from. Alright, then you get to cube roots. Again, this is more so, can you plug it into your calculator and get 3? If you can, great, you're on the right track to using your calculator correctly. Now, I think I've got 2 calculators here with me, so maybe that's what we'll do. We might as well show you how to type these in on the calculator, since that's really what I'm saying over and over again is you should be able to. So the problem is, on this calculator, I don't actually have a regular square root, or I don't have a regular cube root button. Now some of them do. Now on my other calculator, now this one's a graphic calculator, it's a little bit more advanced, but this one also doesn't have a square root button, a cube root button. It has a square root button. So how do I find the cube root of something? Well, let's look at probably what you'll mostly use. There should be one that has something like a x root or a blank cube, like a blank square root. And I know I'm saying square root, but there's a blank square and then a root. And so the idea is you can essentially say, oh, okay, well then, because I wanted the cube root of something, I first type a 3, then I press the blue second button, and click this button, which above it has the blue thing I wanted, and you can see now the 3 I typed first has gone into that little blank box, and I can type in my 27 and get 3. Alright, so that's how it works on this calculator. It's nice because it has what we call kind of math print. If we use even your regular phone calculator, which obviously you can't use on the exam, but some calculators work like this, where you've got numbers that essentially, how do I say it, don't really show up, or it doesn't show the work of what you're doing as you go through it. So in that case, what would I do? Well, this one actually has a cube root button, but I want to look at that y root x button because that's the one you really want to learn how to use. So I'm pretty sure what I would do is I would type 3, then I would say y root x. Oh, nope, so clearly not. It actually is doing kind of some math print there. So maybe I would type the 3, the y root x 27. it goes the other way around. So you can kind of see it's every calculator is a little bit different. So 27 cube root y. So you really need to be careful about how are you typing it into the calculator. See, on the other one, I typed the 3, then the root, then the 27. My phone calculator, or maybe some of your other calculators, might want you to type the 27. Then I'm taking the root of, and then to the third root. So just be aware of that ordering, and that can be kind of tricky to learn. But that's, again, what this section is really here to test you on, is can you plug each of these in and get these answers into your calculator. Okay, moving more quickly then to follow, this one's negative 3, and this one also ends up being 3. Okay, other things you can do, just to say, is I would recommend on your scratch paper, the first thing you do when you get your exam is you write 2 squared is 4, 3 squared is 9, 4 squared is 16, and I would almost go up to 15 squared, which ends up being, I believe, 225. And let me double check. 15 times 15, yep, 225. Okay, after that, you might want to make a list of cubes, and really you don't need to go farther than probably 5 or 6. So 2 cubed is 27. Sorry, thinking ahead. That's 3 cubed. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. 6 cubed ends up being, I believe, 216. And then I would do that, you do your 2 to the 4th all the way up to 5 to the 4th, and then maybe even 2 to the 5th all the way up to 5 to the 5th. And if you list all those out, right, you're writing equals, 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 solving all those, that would be a nice little kind of cheat sheet for you. Just as you see these numbers show up, you'll see what you're getting. So again, I'm going to kind of go through this assuming you have that list set to the side that you're referencing as we go through it. Okay, so we've gone through the how do I type stuff into my calculator section, and now we're moving on to what do we do about things that aren't perfect squares. So this calculator, again, is a little bit more advanced, but if I actually type in the square root of 18, you'll see it by default doesn't even give me the regular decimal number. I have to hit this kind of approximate button on this calculator. So now it says, okay, that's what it is. So yours probably would have spit out the 4.24 whatever. But you can see there's actually an advantage to that. But really, we're just dealing with these numbers that aren't perfect squares. And so we type them in, we get our answer, we move on. What I'm more interested in doing in this section is saying, yes, this is 4.24 and the negative root of 32. So let's type that in. I'm going to type negative first, and then the root of 32. And again, now I have to hit approximate on this calculator. That one's negative 5.65. Oops, back up here. And the cube root of 56. Let's see here. Oops. Cube root of 56. I get 3.825. Or I guess 0.826 when I round. Also, whoops, I should have, that one should have been 0.566. And the other one up above, let me make sure I'm rounding properly to my 2 places. Yeah, it should have been 0.24. This one's 0.66 to 2 places. This one's 826 to 3 places. Just make sure you round to the right place. I'm less concerned with that here. I'm trusting we could do that. Now, what I want to do that's important, though, is I want to understand where was I getting those other answers in the calculator. What were we doing there? And maybe there's even something else to say is, how should I know what the square root of 18 should be? Well, the only thing we have to go on for reference is that 18 is in between 16 and 25. And we know that that roots to 4 and that roots to 5. So it should be between 4 and 5, and it should be closer to 4. And I mean, just to say, that's about all you could do if you had to approximate without a calculator. That's about all the reasoning you can do. But even so, those decimal places, be careful about how they kind of move and grow between those two numbers. It's a little bit different, and it might not be what you expect. So I wouldn't recommend just saying, oh yeah, I'm just going to approximate and guess. But just to give you a reference, that's really the only thing you could do without technology. Okay. Well, then what else can we do about root 18? How can we deal with it? Well, the issue is root 18 is composed of a 9 or rather 18 is composed of 9 and 2. Now, of course, 18 is also composed of 3 and 6, but the issue is 3 and 6 aren't perfect squares, so we're going to ignore, that, I don't want to say interpretation, but that kind of assumption of what could 18 be broken into. So if you notice, what I'm doing or saying here is that if I have a number that's not perfectly square rootable, then I'm going to start breaking down its parts, and I'm going to start asking myself, is there a perfect square hiding inside of my number? And yes, 18 has 9 inside of it. Okay, well then what I can do is I could say, well, what's the square root of 9 and what's the square root of 2? Well, the square root of 9 is 3, that's why I chose it. The square root of 2 just stays because it doesn't get freed up, and there we go. And that is what this calculator conveniently was telling me before. If I square root 18, I get 3 root 2, because there's a 9 and a 2 inside of 18, and 9 square roots to 3, and 2 doesn't square root to anything nice, so it gets stuck inside. So there we go. That's kind of the two ways we can deal with irrational numbers. We either simplify them and just estimate, or we truly simplify them and rewrite them as a simpler form, so to speak. Or rather, we take out any square roots that we can and leave what's left over. So with that being said, that leads us into the next section where we're going to start seeing a few more ideas. Now also, we need to remember what the definition of a square root is. The definition of a square root is what number can be multiplied to itself twice to get you this number. So, or in other words, what thing can I multiply to itself twice and get y to the fourth? And the answer is y squared times y squared. We'll add those exponents and get me y to the fourth. So that means the answer is y squared. Also, right now we're, for the moment, going to ignore this text, but know that it is important for why I'm going to move on some of these examples. Up next, this one's going to be 6m cubed for similar reasons. The square root of 36 is 6, and if I want m to the 6th, then I have to have m cubed times m cubed, right? Something multiplied to itself twice that gets me m to the 6th. This is the thing that multiplies to itself twice to get me that number. All right, up next, moving a little quicker, that's going to be 6 over 5, essentially, right? 36 and 25 root to 6 and 5. X to the 10th will have x to the 5th multiplying to itself twice to get me that. And y to the 4th, we'll have y squared, because we actually already saw that before. All right. Now, this next one is a little bit different, but it's what number can multiply to itself 3 times to get me y to the 9th. And that's going to be y cubed, y cubed, y cubed. That's what I need, so my answer is y cubed, because those multiplied to themselves will add 3 plus 3 plus 3 and get me 9. Last but not least, let's go through this one. This one's going to be 3, because that's the 4th root of 81. And then I'll also have x to the 4th. And what I'm going to do now is I'm going to spoil kind of the next section entirely, but just show you what the deal is, what's going on here. The secret is it's division when you're dealing with exponents and roots. 4 divided by 2 is 2. 6 divided by 2 is 3. 10 divided by 2 is 5, so on and so forth. And then look at this. 9 divided by 3 is 3. 16 divided by 4 is 4. You are doing division to figure this out, and that will even go deeper into 8.3. Okay, now next one, this one's a little tricky, and I'm just going to say this is something that will appear in your homework only. It won't be on your exam, but I want to show you that there is sometimes more than meets the eye on some of these ugly examples. So, let's see here. It now says assume variables represent any number. And the idea is if we just go, oh yeah, it's just division, and we write y to the 7th, we would normally be right, because 14 divided by 2 is 7. But there is an issue, and what I'm going to do for now is I'm just going to say the issue is I need to wrap this in absolute value. Now, what I'm then going to do is I'm going to write down the rule that we need to follow here. Why did I just need to do that? So for this section, the rule is if an even root let me rephrase it. If an even root in, sorry, gosh, I did it again. If an even exponent, there we go, in a root and sorry, there's more qualifying statements now that I'm thinking about it. In an even root results in an odd exponent, use absolute value. Okay, so that's the rule, that's what happened here, and so let's explain it. 14 is an exponent inside of my square root, 2 root. So I've got an even exponent, 14, inside of my even root, my square root, and it resulted in an odd exponent when I did that division. Because of that, I need absolute values, and I'll show you afterwards in a second, but for now, let's just recognize that rule. And let's move on to this example. So 49 roots to 7. Y to the 12th becomes y to the 6th. Now this is an even exponent, and this is an even root, but it resulted in an even exponent, so guess what? I don't need absolute values. Okay, up next I have an odd root, okay, and because I have an odd root, well, an odd exponent in my root, then this doesn't apply because the first step isn't there, so we're good. So 27 cube rooted is 3, and what multiplied to itself 3 times, or in other words, do division, 9 divided by 3 is still 3. Or in other words, I need 3 groups of 3 to make something to the 9th. Okay, so let's really quickly just explain what just happened on that last example and why we needed the absolute values. And to do that, we'll just do it by example. We'll plug in 1. And here we'll let y equal -1. Now notice the reason we have to do this is because it can be any number. Notice up top it said they were non-negative. That's why none of this stuff had any worries about it before. So let's see what we can do. If I plug 1 into the original expression, then 1 to the 14th is 1, and the square root of 1 is 1. From there, what if I plug in -1? -1 to the positive 14th, or to the power of 14 rather, will become +1, and the square root of 1 becomes 1. Now let's compare that with what we said this should be simplified to. So if I just had y to the 7th, then I would have 1 to the 7th, which would be 1. So far those match, that's all good. But if I had -1 to the 7th, and you can take your calculator out, then that would be, let me do this. I realized I wrote this wrong. That's y to the 14th, that's what we're doing there. And then this is just y to the 7th. That's what we're doing afterwards. So I actually didn't need to write that there. Okay. So we had 1 to the 7th, and that's just 1, and we're good. Okay, there's the match. Okay, so again, so far we can see, well, when it's +1, it's fine. +1 raised to the 14th is still +1. Square rooted is still +1. Afterwards, right, the other simplified form, can I still plug in 1 and get the same result? If I plug in 1 and I raise it to the 7th, I still get 1. Let's deal with -1. If I plug in -1 to the 14th, it becomes positive. Square roots is still positive. Now this one, if I have -1 to the 7th, it actually becomes -1. So the issue is, right, these don't agree. And that's why we need the absolute values, because as long as I then wrap this in absolute values, take a look at this, now that's still 1, and now this becomes 1, and now I get my match. So that's why the absolute values are necessary. Otherwise, this original and result won't agree in all cases when you hit your negative numbers. So, again, It's only something just to mention in the homework. We're probably over explaining it, but I just wanted to show you that, yeah, sometimes there is a little bit more tricks than meet the eye, but for the most part, we're dealing with the quote-unquote simpler tricks. We'll skip over that last one, and I think we did that one in the notes. Now, up next, we need to first in 8.2 talk about the big idea here and really explain again that this was division. And the idea here is that when you have something that looks like this, then, and that's what we saw a lot in the last section, right? When I even had, some y to the 14th inside of my square root, I was dealing with that. And it turns out that that can be written in two ways. Number one, you can reorder whether it's being raised or rooted, and those are both equivalent. But the big new idea is that this is the same as this. Now, this actually shouldn't be too surprising because when we have something like this, we're saying the fifth root. Now, the issue there is that, or rather the thing to notice is, where's the only time we say the word fifth? This is 1/5. So, it's the same verbiage, the same vocabulary. So it should not be surprising that if I have a fifth root, then I have a 1/5 in my exponent. That's what we're saying now, is that a fifth root can be written as an exponent of 1 to the 5th. Which is why we can now go back to these calculators and show you something interesting. I don't actually know, usually, where the cube root button is in the calculator, because I would say, I want 27 and I want its cube root. Then I'll take 27 and I will raise it to the 1/3 power, and I still get the same result. I've internalized, right, what a cube root is, and what a square root is as an exponent, and that's usually, to me, the first thing I type, and then I don't need to worry about those special root symbols, and does the 3 go first or the 27 go first? That's the way I've kind of learned it. So just be aware of that. And that's the concept for the rest of this whole section, is they, number one, want you to get used to going back and forth between the two, and then number two, simplify using some algebra afterwards. So the first thing here is that, well, that's the same as the square root of 49, and of course that's just 7. This is the fourth root of 625, and that's just 5. This is the cube root of negative 216, and it turns out that that's going to be negative 6. Now, unfortunately, we start running into some algebra, so here we go. This is the square root of 100 x to the 8th. And remember what we learned before, that the square root of 100 is 10, and then this is really division, 8 over 2, and actually you can really see it here. Remember that exponents to exponent multiply, so this is 8 times a half, or in other words, 8 divided by 2. We get x to the 4th then. Alright, similarly, this is saying I've got the square root of this whole thing. And so that's w to the 4th over 7. I know we're going quick, but hopefully with practice this goes quick for you as well. And again, this is more so there to be your check. This next example is, again, a great time to use your calculator, but we're going to answer this, kind of in the realm of, or a way of saying, what if I didn't have a calculator? What would be the best way to do this? Now, the best way to do this in my mind is would be to say this is the cube root of 27 squared. So notice what I'm doing is I'm opting for this way of writing it instead of this way. So either is valid. You can jump from any one of these three, right? They all work. They all play together, so to speak. You can switch from one side to the other at any time. But the idea is I don't know what 27 squared is in my head. So what I'm going to do is I'm going to say, well, I do know what the cube root of 27 is, so why don't I do that first? That's 3, and then I can square it, and then I get 9. Now, again, you can plug this all in one line into your calculator and just move on and get 9. You should do that. You shouldn't need to work it out step by step, but it's nice to know that you can. Okay, similarly, I would write this as 243 in a fifth root, and then cube it afterwards. 243 actually comes from 3 as a fifth root, and then 3 cubed is 27. Alright, now this next one is tricky, but just remember the one rule. And the one rule is that a negative out front, unless it's wrapped in parentheses, is not a part of your exponent. So that's how we're going to choose to rewrite this. The negative is just there. The over 2 is the square root. And the 5 on top as the exponent is the 5 on top as the exponent. Again, the 5 could go inside on top of the 9, like we have here. But why do that? Because after all, I don't know what 9 to the 5th is. Now, without a calculator, I'm going to say I'm not quite sure what 3 to the 5th is. Other than the fact that I know I already did it over here, and I know I did this in lecture a few times already. So this is negative, and then 243. Again, notice the negative's on the outside, so I raise it to the 5th, and then that over 3 the negative out front just tags along. Alright, we're doing good. From here, we've got a lot of examples to go through. So now we're just going the other route, rewrite it in exponential form. So this is 4/5. Done. Now, even though there's ugly algebra here, it's all wrapped in parentheses, which just means keep the parentheses. This is then 3/4. So there we go. All right. Now, this next part is super important. This is where we really dive into the concepts of this chapter. And what we're doing here is we're going to kind of do chapter 5 and chapter 8 all at the same time. So what I mean by that is we're going to redo those, addition or subtraction rules of exponents and deal with these fraction exponents as well, or rational exponents as well. So that means we're probably going to have to add or subtract some fractions. Okay, so first, what this means is when I'm multiplying, I am adding or combining as is my two exponents. So I usually would add them, put a plus sign between, and I did, but because one of them was negative, the negative is just going to stay. If I work that out, that's y to the 2/4, which means this is y to the 1/2 if I reduce that fraction, which means this is just the square root of y, and either of those are valid. Alright, so not too bad. We're just subtracting those fractions because we did add them or we did combine them, but one of them was negative. Alright, let's look at the next one. The next one, we've got 12, and then we have a to the 1/3 plus 1/6. Now this time, what I'm going to need to do is I'm going to need to create a common denominator. So that'll be a to the 2/6 plus 1/6. And again, that's going to be a to the 3/6, or I'm even just going to write 1/2. Now, careful here, this is 12 square root a. Remember that the exponents were only on the a, not the 3 and the 4. And so in the result, the exponent is only on the a, not the 12 out front. So just be cautious of that. All right. Up next, we've got division now. So let's see what happens here. That means I have y to the 5/6 minus negative 1/6. When you are dividing, you are subtracting your exponents. So I'm subtracting something that already was negative. That will double negate and become positive. This ends up being y to the 6/6, which is actually just y itself with no root because that simplified to 1. So we're good there. All right. Next rule to remember is that when you have a power to a power, they multiply. Also, because this is only one term, there's no pluses or minus here, we can go ahead and, I don't want to say distribute this exponent, but essentially that is what we're doing. So 3 cubed is 27. And if I multiply 2/5 times 3, then I'm going to end up with 6/5 because the numerators multiply. This is really 3 over 1, remember? So 6 and then 5 times 1. Same thing over here. This is going to be b to the 12 over 5. And we're good there. Now what we're about to learn in the next section here is that really this might not be the stopping place you want. But it's okay if they say you can leave your exponents as improper fractions. But you'll see what I mean in the next few examples. All right. Up next, if I have a negative exponent, remember what that means? It means this is really 1 over 25 to the positive exponent. If you have a negative exponent, it can transfer where it is in the fraction. So if it was in the numerator, now it's in the denominator, as long as you switch the sign of that exponent. Well, that means I have 1 over the square root of 25, which means I have 1/5. All right, almost done. That means I now have 36 over 25. If I have a negative exponent over a fraction, it flips the entire fraction and then switches the sign, because you really use that negative exponent on each part. It was on the 25, so it went to the bottom and became positive. It was on the 36, but it was negative, so it moved to the top and became positive. Now they're both positive, so now they're both the same exponent again, and we get 6/5, because that's, after all, what the square root of 36 and the square root of 25 are. So lots of little rules are stacking up and becoming really important to us. Okay, up next, we're in this simplify section. Now, what do we mean by simplify? Well, it depends, I'm going to kind of say. But typically what it means is, and let's say it like this, your fractions are reduced, or your exponents are reduced. You've written your numbers with the smallest base possible, and you've dealt with what I'm going to call mixed numbers. Now, right up here, you can see we have 6/5 and 12/5. What I want to remind you of is that could have been written as 1 and 1/5 and 2 and 2/5, depending on how you want to look at those fractions. Now, we haven't learned what the mixed number version of writing this out is, but just know that that is coming up in the next few examples. So just let that be something we think about, is that if you end up with a mixed number, or rather an improper fraction, there's a way to write it as a mixed number instead. All right, but there's a lot of things going on in these examples, so let's see what's going on. The first one is 64 is actually a number that could be written in a lot of different ways. Now what we're going to do is we're going to rewrite 64 with its smallest component, which is of course 2. I say of course, it's not actually obvious, but it turns out that you can write 64 as 2 to the 6th power. That would be the best way to write this, and break it down into its smallest chunk. So really, again, what are we doing there to do that? We're doing this. We're doing what we call prime factoring. We're saying, okay, I see this 64 here. Does 64 have any smaller parts? Yeah, 2. What am I left with? 32. We keep going down, and it turns out that you just end up getting 6 2's as you rewrite this. So there you go. After that, let's see what's going on here. So if I have 2 to the 6th, right, an equivalent way of writing 64, what happens now? I have 2 to the 6 over 4, which means I have 2 to the 3 over 2, which means, oh, here we go. I've got the square root of 2 cubed. Now here's where we're going to take two different approaches. Let's follow this one down. I could write it like this and choose to say 2 cubed is really a 2 squared and another 2. The reason I would do that is to say, well, 2 squared being square rooted is just 2, and this 2 left over is just 2 as well. But now I want to call your attention to the mixed number approach, that this is 1 and 1/2. Now what does that represent? It represents that there will be a 2 that escaped, 1 2 that will escape to the outside, and 1 2 will be left in the square root on the inside. That's the mixed number approach. So you should be able to see that and jump right to here is essentially what I'm saying. All right, let's see how that works out in a few other examples. This one is first 10 over 6, which is 5 over 3. Now, once again, as a mixed number, that's, let's see here, 1 and 2/3, which means I have 1x on the outside and 2 x's inside the cube root that did not escape. All right, there we go. Up next, this one we can do a little kind of quickly. If you kind of notice the pattern, notice that at first this was 10 and 6, and it reduced to 5 and 3 because they were both even. I'm going to go ahead and just reduce that here. So I'm going to have the 4th root of w cubed y to the 1st. And we're actually done there because none of those are greater than 1. None of those made a mixed number. This is 3/4 and technically 1/4. Not 5/3 or 3/2, not something over 1, right? 3/4 is less than 1, 1/4 is less than 1. So we don't have any mixed number kind of things to deal with here. All right, let's keep going. This is x to the 1/2. This is times x to the 3/4. That means if I get common denominators, I have x to the 2/4 times x to the 3/4, which means I have x to the 5/4. And once again, using my mixed number approach, that's 1 1/4. So there's 1x on the outside, and there's 1x inside a 4th root. All right, so the mixed number approach is super, super valuable to us. With that being said, we'll jump right into 8.3 through 8.5, and these ones are kind of mixed together, and there's a lot going on here, but we're going to see more of that mixed number approach. We're also going to skip over the writing of the rules. Those will be filled out in the notes online. Alright, so the first thing to realize is that what we're doing here is really what we did, let me maybe write it up here, what we did with the square root of 18 in reverse. Remember, with 18 I wrote it as 9 and 2, but the idea was that technically I should write that in one square root, but then the idea that the rule teaches us is that you're actually allowed to write those as each of their own square roots multiplying. Now the key is that they're both still in the same type of root that we started with, and so now really what most of these examples do is they take this idea but they do it in reverse. So we've got 4 and 9. Now actually this one's kind of special because this actually could just be 2 times 3. You can actually root those directly and get 6. But let's follow the rule and say, oh, this is really the square root of 4 times 9. So this is the square root of 36, and that's 6. So in this case, you got lucky because it worked out either way, but sometimes the numbers you have, like maybe let's do another one. Let's say you had the square root of 3 and the square root of 12. See, none of those root nicely by themselves, but then if you put them together, that is 36, and you still get 6 at the end. So that's kind of, to me, the more interesting example is when you have two things that really don't square root at all, but by multiplying together and using this rule, they now do come together and they can square root nicely. All right, let's move on and just see where this rule takes us. So now I've got 20 and I've got x squared, but this is inside of a cube root, so we're good there. So what did I do? Well, I just multiplied them together. They're both cube roots, so 4 times 5 is 20. X times x is x squared. X squared in a cube root is 2/3, not a mixed number, so we left it inside and we moved on. All right, up next, this is going to be the 4th root of 16, and it turns out that you can complete that and you just get 2. All right, up next, let's put these two together. When I multiply these, it's still in the 7th root because that was the same root that they both had. And 9 and 5 will add their exponents to make 14. Well, guess what? 14 over 7 is just 2. So we're done there. All right. Let's keep on going. This one is going to be root 11 over 7. Because, again, the idea here is even though it's one root, it could be written as 2 roots. The root of 11 over the root of 49. And one of them I can root and the other one I can't. All right. Up next, same thing. Because they're both in a 5th root, they can actually just be divided, and I can get 5th root of 3. That doesn't simplify any further, but it looks better than 2 of those roots. Then, this is where we really get into kind of what we were doing with the square root of 18. We can look at 80, and we should ask what the largest perfect square is, but really what we're going to do is we're just going to say, can I find a perfect square? What's any perfect square I can think of? Because you can always re-multiply things to get your largest perfect square. So what I mean by that is you should figure out that this is 16 times 5, but let's say at first you just see 80 and go, oh, well, there's a 4 inside there, and 4 is a perfect square. Well, then circle that perfect square and write what you're left over with. You're left with 20. Then you look at 20 and goes there, perfect square, and that's where you go, oh, silly me, there was another 4 inside of that, with 5 left over. And now maybe you can see what I was saying before. Put those two together by multiplying, because after all we were dividing, so re-multiply them, and I just found 16, my largest perfect square. So it turns out the best way to write root 80 is root 16 root 5, which is 4 root 5. Okay, So I kind of call this method kind of perfect square hunting. You're always looking for a perfect square, looking for a perfect square. Remultiply them back together, you will always get your largest perfect square. Now guess what? It doesn't just work with perfect squares, it works with perfect cubes as well. The thing about this is we've got this 4 to remember to tag along as we go through the problem. But for now, let's look at 448. For cube roots, again, we've got 2 cubed is 8. And although, actually I think it does, 448, does that have an 8 inside of it? Yes, it does. So never mind, forget my although. So I found an 8 that is a perfect cube. Then, guess what? 56 has another 8 and 7's left over. So it turns out the best way to write this is 64. Remultiply those two together. 7. Cube root of 64. Cube root 7. Careful that you're cube rooting 64, which results in 4. And then cube root 7. So now we can go back. Okay, we moved that over here. So let's see here. We had the 4 from before. And now I've got the new 4, cube root 7. So I have 16 cube root 7. Nastiness, nastiness. But again, you can see we're doing that, what I call perfect cube hunting now for that problem. All right. Let's keep going, and this section is going to be where we really need to pay attention to, again, that mixed number idea. So 32 first doesn't square root nicely, but there is a 16 and a 2. Now that means I'm going to be left with 4, because that's what the root of 16 is, and 2 left over on the inside. Now similarly, this is x to the 5 over 2, which means I have 2 and 1/2, and that's my answer. Now those should be written right next to each other in your final answer, but for now I'm not going to write them, directly next to each other. But the idea there is, again, I used the mixed number approach where I said this is 5/2. 5/2 is 2 and 1/2, so 2 on the outside, 1 left in the half root. Let's keep going. So I've got the y cubed from before. There it is. This is 10 over 3. Which is 3 1/3. So guess what? I've got y cubed and 1y left back in the cube root. And so I've got y to the 6th when I multiply those outer ones together. Cube root y left on the inside. All right. With that being said, for time, I think we're going to stop this video here, and then we'll continue on. Yeah, we'll do that.